We present an architecture to answer questions about the content of images, a challenging task that combines scene and language understanding and requires the system to respond to a wide range of natural language questions involving objects, attributes, spatial relations, and counts. Our previous symbolic approaches explicitly build on a chain of perception, knowledge representation, and a formative action system. This solution has a few limitations, hence design ontology, poor scalability, and lack of joint training. In contrast, our new approach facilitates end-to-end joint learning. We combine convolutional and recurrent neural networks to generate multi-word answers conditioned on the image and the question. Our method can answer correctly on a wide range of questions and also improves over a language-only baseline for which we have collected new annotations. The latter setting captures co-occurrences in the question-answer pairs that can be interpreted as a form of common sense. Our new neural-based formulation doubles the performance of the previous approaches on this challenging task. We provide new data and metrics to measure and analyze human consensus on this task.
Segment phrase table for semantic segmentation, visual entailment, and paraphrasing. Recently, great progress has been made at the category level recognition and sentence level associations. In this work, we target phrase level associations, a relatively unexplored direction which achieves a specificity of category level analysis while also maintaining the expressiveness of the high level descriptions. We introduced segment phrase table, which is a large collection of bijective associations between textual phrases and their corresponding segments. Our method leverages web-supervised object localization and co-segmentation for learning segmentation models from web images. Association of segments to phrases allows us to motivate the problem of visual entailment, paraphrasing, and relative similarity, which are used in textual reasoning. Our approach improves entailment results compared to a language baseline. Also, we obtain better results in visual paraphrasing and relative similarity. In addition, SPT allows linguistic constraint to be incorporated into semantic image segmentation.
Hi everyone, I will briefly introduce our work learning Korean image similarities with ranking canonical correlation analysis. Our framework starts from user click through data of image search engine. A bipartite graph between queries and images is then constructed. Next, canonical correlation analysis is performed for mapping image and query into a common subspace. Furthermore, as click-through data conveys relative relevance judgments, a bilinear similarity function is learned where the subspace is fine-tuned to respect this preference. Finally, the query and image similarity is measured by this bilinear function, and the similarity between images can be defined as dot products and the learned subspace. A large-scale image dataset, our model is shown to be powerful for both keyword-based and query-by-example image search tasks. Thank you for your attention, and welcome to my homepage for more details.
Graph mining is a general method to discover common patterns in different data, such as texts, 3D points, videos, and images. We can use a large graph to represent an image, use array attributes to describe local patterns, and pairwise attributes to describe the deformable structure. Therefore, the mining of the common subgraph pattern among images is equivalent to object discovery. Our method discovers a three-layer and/or graph to represent the hierarchical pattern structure, including structural knowledge and alternative local patterns. Variations in texture, rotation, scale, illumination, and structure can be simultaneously encoded and discovered. Our method has broad applicability. We can design different array and pairwise attributes to represent different data, and apply our algorithm to different tasks. The code will be available online. Please visit this website.
Is not built for computers to process and understand big data with temporal changes. It's often presented in the form of weighted sequences with spatial properties in both space and time. Such spatial properties imply non-completed patterns are repetitive and thus can be sparsely represented by some dictionary. Unfortunately, a direct code of current dictionary learning methods would encounter problems in image computational scalability and correlated spatial temporal information. To address the problem, we propose to directly handle the input of tensor data without categorization and structure dictionary with separability and scalarity. The resulting sparse coding is simply one-step thresholding and the dictionary update is by a series of small-scale SODs. With the learned dictionaries, we extract unique characters while sparse coding on test samples, and compute special temporal histograms on sparse codes. All method works very well on two different databases. One is UCL and the other is Dytex. Besides, our feature extraction process is the fastest compared to existing methods. That's all. Thank you.
In this paper, we focus on the problem of image restoration such as image super-resolution and denoising. We utilize sparse representation technique to solve this problem. Obtaining an appropriate dictionary is the key point when applying sparse representation. We have the observation that preserving the data structure during sparse coding by building relationships of samples can enhance the recovery performance. In this paper, we introduce conformal constraint and low-rank constraint to achieve the structure preservation. Finally, we obtain dictionaries with better representation ability and compactness. Our approach can be applied to image restoration tasks including image super-resolution and image denoising, and extended to video recoloring. Our approach can learn a better dictionary with competitive performance compared to the previous methods. Thank you.
Welcome to our thumbnail generation project. We usually want to show an image gallery in the Windows Explorer. A common approach is to directly scale the images. However, it will be hard for us to recognize the foreground. For example, we can hardly recognize the animal in this thumbnail. To solve the problem, we introduce cropping technique with image scaling. Basically, we scale down the image and crop it with the fixed window. As a result, the thumbnail is better. Our technique is based on two essential considerations. The first one is visual representativeness. In this image, good thumbnail should contain the sky, mountain, and human body. The second one is foreground recognizability. The lotus in the good thumbnail is easier to be recognized. Our algorithm will generate several thumbnails and predicts the scores for all candidates. After that, we only keep the result with the highest score. Finally, we can generate better thumbnails for image gallery.
In this project, we propose to learn optimal filters for color image reconstruction based on non-linear spectral decompositions. We add noise to all images in a training database and spectrally decompose them. The optimal reconstruction filters are learned in such a way that they combine frequencies of all different color channels. For a given noisy image, we again apply the spectral decomposition and use our learned filters to obtain an estimate of the true noise-free image. Our proposed method outperforms BM3D qualitatively as well as quantitatively at high noise levels. We would be happy to discuss details and extensions of our framework at ICCV.
Natural images are intrinsically sparse in many domains. These domains can be represented by a dictionary. We learn an adaptive dictionary from the noisy hyperspectral image and exploit local and non-local sparsity to design a denoising model. First, cubic patches are extracted from the hyperspectral image in an overlapping pattern. Then, all band images from the cubic patches are clustered in the spatial domain. The spatial bases for each cluster are then learned independently. In the spectral domain, all spectral distributions from the entire hyperspectral image are used to build the spectral PCA basis. The adaptive spatial spectral dictionary is derived from the spatial and spectral bases, where each cluster has its own spatial spectral dictionary. Here are some results.
We present a technique for correcting the color of an image. Under certain conditions, tinting an image results in a translation of a log chrominance histogram of that image, as shown here. This insight lets us train a convolutional classifier for white balance, similar to how one might train a sliding window classifier for object detection. In short, we show that white balance is reducible to object detection. We train our model to discriminate between white balanced images and poorly white balanced images, resulting in a log chrominance histogram filter. At test time, the input image is turned into a log chrominance histogram, which is then convolved with our learned set of weights, resulting in a probability distribution over likely white points. The most likely white point is then used to untint the input image. On standard benchmarks, we outperform the state of the art by nearly 40%.
We present a novel sampling-based image mapping method. For an input image and user-defined tree map that determines certain background and foreground regions, our purpose is to compute alpha-mat values for unknown regions. Our method. Firstly, we group the image pixels into superpixels and then construct a dissimilarity matrix in which each element denotes a pairwise distance between unknown and known superpixels. We propose a KL divergence-based dissimilarity measure between two superpixels to compute pairwise distances. Our statistical distance measure provides better discrimination than mean color distance of superpixels. In the last step of sampling process, we use a recent dissimilarity-based sparse subset selection algorithm to obtain representative foreground and background color samples. Here some image composition results.
we present a method to predict semantic boundaries. Our method can be viewed as a high-for-low approach where we use high-level object features as cues for a low-level boundary detection task. We also showed that we can apply our boundaries to the high-level vision tasks. This in turn can be viewed as a low-for-high scheme where boundaries serve as low-level cues to aid high-level vision tasks. Our approach can be described as follows. First, we extract a set of candidate points. We then upsample the image and feed it through 16 layers of pre-trained VGG network. Finally, we perform feature interpolation and feed the resulting vectors to the two fully connected layers to get a final probability map. For the boundary detection task, our proposed method outperforms all of the prior methods. Also, using our boundaries, we improve performance for semantic boundary classification, semantic segmentation, and object proposals. To summarize, we present a boundary detection system that is accurate, efficient, and applicable to high-level vision tasks.
An irritating type of video degradation, called yang phasing, is spatially patchy and temporally inconsistent object appearance, with parts of the scene turning in and out the state of underexposure or overexposure, back and forth. Such effects are quite common in impromptu make videos as shown now. The YYP effects are caused by unevenness of illumination, changes in the directions of incident and reflection lights due to object and camera motions, conditions that confuse camera's auto-exposure. We develop an algorithm to remove the undesired YYP effects. It restores the video as though it was shot in spatially uniform and temporally steady lighting conditions. The YYP removal problem is formulated and solved as an interframe, spatially adaptive, optimal tone mapping problem. We retain the temporal consistency of total reproduction by mapping the intensity histograms of input frames of a given scene to a common target histogram.
Hello everyone, I'm Dingwen Zhang, a PhD student in Northwestern Polytechnical University. I'm so honored to introduce our work on causality detection here. Causality detection is an emerging topic aiming at discovering the common and salient objects from the given image groups, with implying priorities based on the human visual attention. To alleviate this problem, we naturally reformulate it as a multiple instance learning program and further integrate it into a self-paced learning regime. This framework on one hand is capable of fitting in statistical metric measurements and discovering common patterns under covalent regions in a self-learning way, and on the other hand, it tends to promise the learning reliability by simulating the human learning process. Comprehensive experiments have demonstrated the effectiveness of the proposed framework. Finally, welcome to our poster for further discussion.
Hello everyone, welcome to our spotlight. Currently, various imaging modalities such as CT, T1 MRI, T2 MRI, etc. are being used for medical imaging research. Due to variations in the image characteristics across modalities, image analysis algorithms trained with data from one modality may not work well when used in a different modality. A straightforward way to address this issue is to collect a large amount of training data in each modality, which is impractical as collecting medical images is both time consuming and expensive. To address this issue, various cross-model medical image synthesis approaches have been proposed in the recent past, which generate subject-specific scans in the desired target modality from the given source modality images. However, most of the existing approaches require training data in both source and target modalities from the same set of subjects. Unfortunately, the availability of such paired training data is limited in many cases. To address this issue, in this work, we propose the first unsupervised cross-model medical image synthesis approach that works without paired training data. Please visit our poster for more details. Thank you.
The title of this work is Weakly Supervised Structure-Output Learning with Flexible and Latent Graphs using High-Order Loss Functions. The main motivation of this work lies in the development of a fully automated system that can estimate the proportion of hypoxic regions from a tumor using the IF and HE images of a tumor, as shown in this figure. There is evidence that shows that this estimation is important for the assessment of the outcome of common cancer treatments, such as chemo and radiotherapy. The development of a fully automated annotation is challenged because the manual annotation for training the system consists only of the high-level annotation, where we don't have access to the underlying graphical annotation. In this paper, we propose two methodologies for solving this problem. In both approaches, we assume the existence of an underlying latent graph with variable structure and variable number of nodes. Our results show that both methods have high correlation with respect to the high-level manual annotations. The database used in this work will be publicly available. Thank you.